Hello everyone, and welcome to our Calculus II final exam review session. Today we'll be reviewing a full-length recent final exam from Calculus II, and I hope this will help you guys to study for your upcoming final exam, and hopefully you'll all do well. Okay, so the first problem we're going to be looking at is an integral, and it appears to be a u substitution. Okay, so what we'll do is we'll have our u equal to 1 plus the square root of x. That means our du will be in derivative of our u, so that would be a 1/2 x to the negative 1/2 dx. Okay, if we're just going to rewrite that, so that would be 1 over 2 radical x dx. So we see in our problem we have a 1 over radical x. We don't have that 2 there. What must have happened? Well, we must have multiplied by 2. So if we multiply both sides by 2, then we can cancel the 2's, and we'll have 2 du equal to 1 over radical x dx. Okay, so now we can make our u substitution. We have integral. We'll have 1 over, this will be u squared du. Okay, now the 2 du would go in. The 2 I could put in front of the integral. Okay, and so now as I'm integrating, keep in mind I can rewrite the 1 over u squared as u to negative 2 du. Okay, so as I integrate that, I know I will get 2 and then add 1, so our power rule, add 1, so we would have negative 2 becomes negative 1, divide by negative 1, which means we would have, if we're just going to rewrite this, negative 2 over u plus c, substitute back in, so that means we would end up with negative 2 over 1 plus the square root of x plus c. Okay, and that would be it for that problem. Let's take a look at our next one. Okay, this one appears to be integration with partial fractions. Okay, so what we need to recognize is we can factor the denominator. Okay, so we'll have we could pull out an x, right? Factor out an x, so x times x minus 2. And so when we split this apart, we know that we'll have some number over x plus some number over x minus 2. Okay, so how does that work? Well, we're going to be multiplying each of these fractions with the opposite, with the other fraction's denominator. Right, so the a over x will multiply by x minus 2. And the b over x minus 2 will multiply by x. Okay, so that way we have a common denominator of x times x minus 2, and we can focus in on the numerator. Okay, we'll distribute the a to both terms in the x minus 2. Okay, so we'll have ax minus 2a plus b times x, and this will equal our original numerator of 4. So now we're going to take a look at what we have. We have x terms and we have constant terms. Now in our original numerator, there is no x term. So we know that if we're just taking our x's, our x to the firsts, that's going to be ax plus bx. So a plus b, and there's no x's, so that'll equal 0. X to the 0, those are our constants. We have a negative 2a equals a constant of 4. Okay, so that's going to allow us to solve for a. We could divide by negative 2. So that means a will equal negative 2. Plug that into the top for the a plus b equals 0. So we have negative 2 plus, and we know b must be then positive 2 to equal 0. Okay, so b equals positive 2. So when we go to set up our integral, now we could replace a and b. So we have integral negative 2 over x plus 2 over x minus 2. Okay, and we can integrate this, and when we integrate, we recognize if we integrate negative 2 over x, that would just be negative 2 times the natural log of x plus 2 times the natural log of x minus 2, and of course plus c. Okay, and that would be it for that problem. Okay, let's take a look at our next one. Use the disk method to find the volume of the solid generated by revolving the region bounded between the curves y equals 2 over x, y equals 0, x equals 1, and x equals 4. And we're going to revolve that about the x-axis. Okay, so to do disk method, remember we're going to be setting up an integral of pi times our function squared, and we're going to integrate with our limits of integration from a to b. Okay, so this function, if we graph it very briefly, it would appear to be a decreasing function, and we're bounded by x equals 1, x equals 4. So let's say 1, 2, 3, 4. And so we'll be between 1 and 4. Okay, so it'll be this region, and we're going to be spinning this about the x-axis. And so if we do that, we'll do our setup. Integral will be from 1 to 4 pi 2 over x as our function squared dx. If we square this, 2 squared will be 4, x will be x squared, so we end up with pi over 4 x squared dx. Now what we can do is pull the 4 and the pi outside. Okay, so we'll have a 4 pi, and that would be on our outside of our integral, 4 to 1, 1 over x squared dx. Okay, now for our integration, to make it a little easier, we can make that 1 over x squared become just x to the negative 2, right? Use our negative exponent property and just say this is x to the negative 2 dx. Okay, so to integrate, use our power rule, add 1 to our exponent, divide by that same exponent, so we end up with 4 pi x to the negative 1 over negative 1, and then we will plug in our limits of integration. Okay, so let's come back over here. We have that would translate to 4 pi. The x to the negative 1 would be a 1 over x. And so now I can just plug in my 4 and 1. Okay, so for negative 4 pi, 1 over 4, right, plug in the 4 first, minus 1 over 1. So negative 4 pi, 1/4 minus 1. Well, that would be like saying 1/4 minus 4/4. So that's a negative 3/4. Simplify, that would allow us to cancel our 4's. And then we have a negative 3 times a negative pi. And so we end up with 3 pi. And that's about it. Okay. Let's take a look at our next one. Length of the curve. Okay, so an arc length problem. Okay, just remember our typical formula for arc length. Okay, from A to B, integral square root of 1 plus our derivative function squared. Okay, and so now, so to make this a little easier, let's get our derivative. So we will have our power rule, 3/2, bring that in front, x plus 5/9, drop the power by 1, so that would be to the 1/2, and then we would multiply by the derivative of the inside, which is 1, so that's not going to change anything. Okay. So now let's go ahead and set up our integral. They have us going from x equals 0 to x equals 8. Okay, so the integral will be from 0 to 8, square root 1 plus 3/2 x plus 5/9 to the 1/2. And then we're going to be squaring this. And we integrate with respect to x. Okay, so squaring the square root, that would cancel. And then squaring the 3/2, we would end up with 9/4. Okay, so our next step, integral 0 to 8, 1 plus, this will become 9/4, and then the x plus 5/9. Okay, with no exponent. Alright, next, we're going to distribute inside the square root. So we'll have 1 plus, that would be 9/4 x. And then multiply 9/4 times 5/9. The 9's will cancel, so we'll end up with a 5/4. Okay, now we combine like terms. We have a 1, which will turn into a 4/4, plus the 5/4, so we end up with a 9/4. Okay, so that means we would have 9/4 x plus 9/4. Okay. We can factor out a 9/4 while inside the square root. And then we can actually take the square root of the 9/4, right? We can pull that outside. So square root of 9 is 3, square root of 4 is 2. So we would have a 3/2 integral from 0 to 8 of the square root of x plus 1. Okay, now we could actually integrate our square root of x plus 1. Okay, so we would just recognize that it would be like a u substitution. If our u is x plus 1, then our du is dx. So we would have 3/2 integral u to the 1/2 du. Okay, integrating, adding 1 gives us 3/2. So we would have 3/2 u to the 3/2, and then we would divide by 3/2 or multiply by 2/3. And so what happens as a result, our 2/3 and 3/2, these would cancel. So we have u to the 3/2. Okay, substitute back in. Our u was x plus 1. Okay, so we have x plus 1 to the 3/2. And then we would evaluate our limits of integration. Plug in 8. Minus plug in 0. That's 9 to the 3/2 minus 1 to the 3/2. So when we evaluate this, just remember the denominator for that exponent, that's your root. So you're taking the square root and then you're going to raise it to the 3rd power. Okay, that would probably be the easier version. You could also take the 9, cube it, and then take the square root, but that would be a little more difficult. Take the easier route here. 9, take the square root, which is 3, and so now you have 3 cubed. 1 to any power is 1. Okay, and so we end up with 3 cubed, which is 27, minus 1, end up with 26 as a arc length. Okay, let's take a look at our next problem. Next one, we have integral of x times sine of 2x dx. Okay, this appears to be a integration by parts. Okay, so we need to set up our u and set up our dv. So u is x, dv is sine of 2x dx. That means du is derivative of x is 1, dx, integral of dv is v, and this would be cosine of 2x, but offsets the derivative of 2x is 2, and integral of sine is negative cosine, so this will be negative 1/2 cosine of 2x and that would be it. So remember, integration by parts will be uv minus integral of v du. Okay, so take our u and our v. So this will be negative 1/2 x cosine of 2x. So that's our uv minus integral of v du. So negative 1/2 cosine of 2x dx. Okay, we could pull the negative out to make this negative a plus. So we have negative 1/2 x cosine of 2x plus integral cosine of 2x dx. And we might as well pull the 1/2 out as well. Okay, so now we can integrate. We have still the negative 1/2 x cosine of 2x. Now when we integrate the cosine, we get the sine, but to offset the derivative of 2, we're going to multiply by a half. So this half times the half would make it a fourth. So sine of 2x, and then that would be a plus c. Okay, if you're ever not sure of these, take the derivative. Right here you do a product rule, and here you could do a derivative, normal derivative. Combine them together, you should end up with the function that we started with. Alright, let's take a look at our next problem. Okay, this appears to be integration with trig substitution. Okay, so you have to remember your triangles. If we have a constant minus an x squared, okay, this will turn into our triangle where our substitution is the sine. Okay, so this triangle will look like the triangle that we typically have with the sine substitution. So here for theta, this would be our x. This is a squared, so a would be 2. And then our bottom leg here would be square root of 4 minus x squared. Okay, so again, x would equal 2 sine theta. Dx, if we take the derivative, would be 2 cosine theta d theta. Okay, and now we can set up our integral. Okay, the dx I'm going to put on top. That is our 2 cosine theta d theta. For our bottom, we have 4 minus x squared. So that would be 4 minus, now when we square our x, 2 sine theta times 2 sine theta, that would be 4 sine squared theta. And then this will be to the 3/2 power. So raise it to the 3/2. Okay, we're going to simplify a little bit. We'll have 2 cosine theta d theta. Denominator, pull out the 4 while inside our parentheses. Okay, keep in mind 1 minus sine squared, we can substitute cosine squared. Okay, so we'll have 2 cosine theta d theta over 4 cosine squared theta to the 3/2. Okay, so at this point we can take a square root, Right, the square root will allow us to simplify 4 cosine squared. Square root of 4 is 2. Square root of cosine squared is cosine. Okay, so that'll end up becoming, still have 2 cosine theta, d theta on top. And then we would have 2 cosine theta. And so that square root is gone now, and this will just be cubed. Okay, so now we can actually simplify and cancel 2 cosine theta from top, and on the bottom we could cancel, we actually have three of these 2 cosine thetas. Alright, so cancel 3, make it a 2, and then we'd have a 1 on top. Okay, so now we have 1 over 2 cosine theta squared. Okay, now 2 cosine theta squared would just be 4 cosine squared theta. And so the 1/4 we could pull out. And just remember, 1 over cosine is secant. So 1 over cosine squared would turn into secant squared. Okay, so we have 1/4 integral of secant squared theta. And that's an integral we should know. Integral of secant squared is tangent. So we end up with 1/4 tangent theta plus c. And remember, one of the things we do is we convert back to our original variables that we started with. So we're going to convert back to x's. So let's use our triangle. So those were the triangles important. We're just going to go back and figure out what is the tangent of theta according to our triangle. So tangent of theta would be opposite over adjacent. So that would be x over the square root of 4 minus x squared. Okay, so 1/4 x over the square root 4 minus x squared plus c. Okay, and you can combine the 1/4 with our tangent function here, so this would be just x over 4 times the square root of 4 minus x squared plus c. And that's it. Let's take a look at our next one. Okay, find the first 3 terms in the Taylor series of the function f of x equals x cubed plus x, and is centered at a equals -1. Okay, so if we have f of x equal to x cubed plus x, we need to figure out what is f of -1 to get our coefficient. So that would be plugging into the function -1 cubed plus -1. So that gives us -1 minus 1, so -2. Next, to get our next coefficient, take the derivative. That's 3x squared plus 1. Plug in -1. So that is 3 -1 squared plus -1. 1. So that'll change our coefficient there, so that'll give us 4. Okay, so I just misread that. Okay, next, second derivative, 2 times 3 That'll give us 6, so 6x. Plug in -1. 6 times -1. That will give us -6. Okay, so to set up our first three terms, okay, we got the first coefficient, -2, plus, next would be our 4, this would be over 1 factorial times x plus 1, minus, the next coefficient would be a minus 6 over 2 factorial times x plus 1 squared. Okay, and we can simplify it slightly, so we have -2 plus 4 times x plus 1 minus 6 divided by 2 is 3 times x plus 1 squared. So those will be the first three terms. Okay, and you don't have to distribute and combine, you just leave it just like this. Okay, determine if the following series converges or diverges. If it converges, find its sum. Okay, so it looks like it's a possible geometric series. Let's take a look at what we have here. We have sigma 2 to the 2n plus 2. We could write that as 2 to the 2n times 2 squared. That would be just undoing our product rule for exponents. Right, so what does that mean? Well, this is a 4. That's a 4. And that's going to be multiplied by, we could say this is 2 squared being raised to the n. So that'll be 4 to the n. Okay, at the bottom we have 5 to the n for our denominator. Okay, so we could rewrite this series n equals 0 to infinity as 4 times 4/5 to the n. Okay, now that's our ratio, right? That's our common ratio. So that means, remember, if that absolute value of the common ratio is less than 1, we have a convergent geometric series. And so as a result, we can use the formula to figure out the sum for a geometric series. Right, so that formula for the sum would be our first term in the series, a, divided by 1 minus r. Okay, so 1 minus our common ratio. Okay, so let's do it. We have our first term. If we plug in 0, so a would turn out to be 4 times 4/5 to the 0, which is 4 times 1. So first term is 4. So now we have s equals 4 over 1 minus 4/5. Okay, so that would mean we have 5/5 minus 4/5, so that's a 1/5. Okay, divided by a fraction, which means we can multiply by its reciprocal. So our sum for this series would be 20. Okay, let's take a look at our next one. Use the ratio test to determine whether the series converges or diverges. Okay, so ratio test, remember, is our limit as n goes to infinity of our an plus 1 over an in absolute value, and that limit is equal to rho. Right? So the Greek letter rho looks like a P. Okay, and remember, if rho is less than 1, so if that limit is less than 1, we converge. If the limit is greater than 1, we diverge. And if rho is equal to 1, inconclusive. And so as a result, we would use a different test to see if it converges or diverges. Okay, so limit. Let's do the n plus 1. So that would be n plus 1 times n plus 1 factorial over 2 to the n plus 1, and then that would be n plus 1 plus 1, so n plus 2 factorial. Okay, instead of dividing by an, we're going to multiply by the reciprocal of an. Okay, this is our an, so denominator on top and numerator on the bottom. Okay, we could expand a little bit in order to simplify. So we still have n plus 1. N plus 1 factorial will be n plus 1 times n factorial. 2 to the n plus 1 would be 2 times 2 to the n. N plus 2 factorial will be n plus 2 times n plus 1 factorial. And then we'll just copy the an. And now we could cancel numerator, denominator, common factors. Okay, so we could cancel n plus 1 factorial, n factorial, 2 to the n, and I think that's it. Okay, so we would have limit n plus 1 times n plus 1 our denominator would be 2 times n plus 2. Okay, so what is that limit going to be? Well, we could expand and FOIL the numerator. We have n squared plus 2n plus 1 over 2n squared plus 4n for our denominator. Okay, and to do a limit as n goes to infinity, remember you have a couple options. You can take the coefficients of your leading terms, right, as long as they're written in decreasing powers, or you can divide by the largest term. You can divide by n squared across everywhere. And so we see that we have 1. This will be a 2 over n, which as n goes to infinity would go to 0. 1 over n squared would go to 0. This will be 2. And then 4 over n would go to 0. Okay, so that means our limit would be 1/2, which is less than 1. And so therefore this would converge. according to our ratio test. Okay, next one. Use a comparison test to determine whether the series converges or diverges. Okay, this one we'll do our comparison. This will be our AN, our BN. We could just take our dominant terms. So we have n over the square root of n to the fourth. Okay, so if we do and simplify, that would be n over square root of n to the fourth is n squared. Simplify further, n over n squared is 1 over n. Okay, and 1 over n, we have studied that it's a p series, right, where p is equal to 1. So if p is less than or equal to 1, we know that it diverges. Okay, so that's what we're going to be comparing to. We could do a simple limit comparison test. Okay, so we can take limit as n goes to infinity of an over bn Alright, and if we get a finite limit, we say that whatever happens to bn, an will do the same thing. Okay, and so let's see if we get that finite limit. Okay, so limit, we would have our n over square root n to the fourth plus 4n squared plus 1. We're doing divide by bn, so our bn is 1 over n, or we could multiply by n over 1. Limit as n goes to infinity, n squared over n to the fourth plus 4n squared plus 1. Okay, take the limit. Inside the square root, we can divide by n to the fourth. Outside the square root, we could divide by n squared. So what do we end up with? We have 1 on top. N to the fourth over n to the fourth is a 1. These will be 0. Okay, we have a finite limit of 1, which means whatever happens to bn, same thing happens to an. bn diverges, so an will diverge by limit comparison test. Okay, our next one. Okay, it looks like we have a improper integral. We'll take a limit. We're going to introduce a variable as b goes to infinity, 1 to b, and this will be 1 over x squared plus 3x plus 2. So what we'll do is we will split apart by first we're going to factor. So the x squared plus 3x plus 2 would turn into x plus 1 times x plus 2. Okay, so focusing in on the fractional integrand, we can set up as a partial fraction scenario. Okay, we'll have a over x plus 1 plus b over x plus 2. Okay, focus on those first, and then we'll set up the rest of the integral later. So again, we're going to multiply by the other fraction's denominator. So multiply by x plus 2 on the left. And then multiply by x plus 1 on the right. Okay, you're going to focus in on your numerator. Distribute the a to that first one, b to that second one. And so we have ax plus 2a plus bx plus b, and this will equal our original numerator, which is 1. Okay, so x to the first powers, we have ax plus bx, so a plus b, and there's no x's in our original numerator, so a plus b is 0. Our constants, we have 2a plus b, so 2a plus b equals, we have a constant of 1. Okay, now to solve this, we can multiply the top equation here by -1. So that'll give us -a plus a -b equals 0. And then we can add. So that gives us 2a minus a is a. -b plus b, those cancel. So a equals 1. If a equals 1 and we have a plus b equals 0, b is going to equal -1. Okay, so that means we'll have our integral. Right, our integral will be integration of, jumped ahead, limit as b goes to infinity of 1 over x plus 1, and then b is -1, so we can say minus 1 over x plus 2. Okay, next we could easily integrate those. They appear to be both as ln's. Right, these would be in the form of an ln. So we would have, and continue up here, we have limit as b goes to infinity ln of x plus 1 minus ln of x plus 2. And this was a 1. Okay, so now we will plug in. Well, actually we could condense this a little bit. We have a subtraction. We could use the property for logs. When we have a subtraction, we could condense it as a division. Okay, so limit as b goes to infinity ln of this will be x plus 1 over x plus 2. Okay, so we have limit as b goes to infinity ln of b plus 1 over b plus 2 minus ln of 1 plus 1 over 1 plus 2. Okay, so taking the limit, we would see that this limit would go inside here of this argument, this would be close to 1, right? We divide everything by b. So the 1 over b would be 0, 2 over b would be 0. This would be a ln of 1. Now ln of 1 is 0. And then we have a minus ln of, and then we simplify here, 2 over 3. So a minus ln of 2/3. Okay. Next we have a work problem involving a force is applied to move an object along the x-axis from x equals 0 to x equals 4. Find the amount of work done. Okay, so as long as they gave you the function, integral will be fairly straightforward. We would have an integral. They give us our bounds, 0 to 4, of x over x squared plus 9. Right, our typical work integral is going to be a to b of f of x dx. Okay, so fairly straightforward. This will be of the form of a u substitution, okay, where u is equal to x squared plus 9. du would be 2x dx. We don't have 2x dx, we have an x dx. So what must have happened? That means we must have multiplied by 1/2. Okay, so that means we have 1/2 du equals x dx. Okay, so let's substitute. So we have the 1/2 we could pull outside. And then we have a du over u. So this resembles our ln integral. Okay, so this means we have a 1/2 ln of u when we integrate. Okay, substitute back in. So we have 1/2 ln of x squared plus 9, and then we will plug in 4 and 0. Okay, so let's plug in the 4. So we have 1/2 ln 4 squared plus 9 minus 1/2 ln of 0 squared plus 9. Simplifying further, that's 16 plus 9, so 25, and 0 squared plus 9 is 9. Okay, so keep in mind our 1/2s in front we could use as a exponent. So we would have ln of 25 to the 1/2 minus ln of 9 to the 1/2. And the 1/2 power is a square root. So square root of 25 is 5. Square root of 9 is 3. And finally we could rewrite that as a division of the 5 and 3. So ln of 5/3. Alright, evaluate the integral secant square x tan x. Okay, so it's just a matter of picking the right u. Okay, this will be a u substitution. So it looks like we have the u as tangent, and then the du would be the secant squared. So u is tan x, du is secant square x dx. Okay, so that's all there. So we have integral of u du, integrate it, so we have u squared times a half, substitute in 1/2 tangent square x plus c. Okay, so that's one you guys would call light work, right? Warm-up set. Alright. Alright, part B. Determine the radius of convergence and the interval of convergence for the power series. Okay, so a typical way we would do this one is with a ratio test in the beginning. And then we would set up our interval, and we would figure out our interval of convergence. Alright, so let's get started. We have limit as n goes to infinity. We have the an plus 1. So we're going to do absolute value, so those negative ones would go away. Okay, we'll have x minus 1 to the n plus 1 over square root of n plus 2 divided by an, or multiply by the reciprocal, square root of n plus 1 over x minus 1 to the n. Okay, split apart the x minus 1, so we have x minus 1 times x minus 1 to the n. And then rewrite the an portion. And now cancel. We have x minus 1 to the n's. Those would cancel. So we have limit n goes to infinity of x minus 1 times n plus 1 over square root of n plus 2. Okay, so this limit as n goes to infinity will be close to 1. Okay, so this will be 1. If we divide by the square root of n, we'll have a 1 over 1. These will be 0 and 0. So this will be just 1. Okay, so next, limit as n goes to infinity, we'd have the absolute value of x minus 1, and because we are looking for the interval of convergence and radius of convergence, we set this to be less than 1, because that's the condition for convergence in ratio test. Alright, set it to be less than 1, and now we set it up as a compound inequality without the absolute value. So set up x minus 1 less than 1, less than on the other side, and the opposite negative 1. So we solve for x in the middle, plus 1 across the board. And so we have 0 less than x less than 2. So now we have to test 0 and we have to test 2. So what does that mean? It means we go back into our original function when x equals 0. Let's plug in -1 to the n, and then 0 minus 1 to the n over square root of n plus 1. Simplifying that gives us -1 to the n times -1 to the n. Okay, now you have here a -1 times -1, which is a 1. So we have a summation 1 over the square root n plus 1. Okay, so that would diverge. You're going to look at it like a p-series, where p is a half, right, where p is less than or equal to 1. And so we know that as a result, it diverges. Okay, let's take a look at when x equals 2. So plug 2 in. So that means we have absolute value of -1 to the n times 2 minus 1 to the n over the square root of n plus 1. Okay, so that gives us -1 to the n, 2 minus 1 is 1 to the n, so we have just -1 times 1 is -1. Okay, so now we think about what this would do. So if we used alternating series test, so remember the alternating series test, you'd have your un would be 1 over square root of n plus 1. So these terms would be positive, right, as we go to infinity. They would be non-increasing. So we'd have 1 over square root of 2, 1 over square root of 3, 1 over square root of 4. Yeah, these would be non-increasing. And then limit as n goes to infinity of 1 over square root of n plus 1. Yeah, if we put infinity in there, as n gets larger, 1 will stay the same on top. So this limit would go to 0. Okay, so this checks off the boxes for alternating series test. So we could say converges by alternating series test. So that means when x is 2, we would converge. So interval of convergence, 0 to 2, including the 2. And then our radius of convergence, okay, so difference 0 to 2, it's the diameter, take half of 2, so radius is 1 for our radius of convergence. Okay, let's take a look at our next one. Area of the polar region that lies inside one loop of the curve r squared equals 4 times the sine of 2 theta. So remember, our formula for area inside a polar region would be integral from alpha to beta of 1/2 r squared d theta. Now our formula is already in r squared, so we don't have to worry about squaring it, and it's just a matter of figuring out our angles. So our angles are going to be from 0 to pi over 2. Okay, that's going to cover that one loop. Okay, so we just have 1/2. We put that outside. 0 to pi over 2. And then we would put our r squared, which is the function as it is. So 4 sine theta d theta. Okay. Now, if we pull the 4 out, that would make that a 2 integral 0 to pi over 2 sine of 2 theta and so when we integrate, integral sine is negative cosine. There's a 2 theta involved, so multiply by negative 1/2 cosine of 2 theta, and then we'll plug in pi over 2 and 0. Okay, so that simplifies to just negative cosine of 2 theta so that would give us negative cosine of 2 times pi over 2 minus negative cosine of 2 times 0. Okay, so negative cosine of the 2's would cancel, pi, plus cosine of 2 times 0 is 0. Okay, so cosine of pi is negative 1. Cosine of 0 is 1. Negative of negative is positive, so we have 1 plus 1. So we end up with area of 2. Alright, and then our last one, equation of the line tangent to the curve, x equals 4 sine t, y equals 2 cosine t at the point t equals pi over 4. Okay, so we're dealing with parametric equations. We would have dy dx, remember dy dx, we need the slope, but that would be dy dt over dx dt. Okay, so we need to take the derivative of the y function. So derivative of 2 cosine t would be negative 2 sine t over dx dt. So derivative of 4 sine t would be 4 cosine t. And now we plug in our t value, pi over 4, to get the slope at that point. So negative 2 times sine of pi over 4 over 4 times cosine of pi over 4. So that gives us negative 2 sine of pi over 4, square root 2 over 2. Cosine of pi over 4 is also square root 2 over 2. So that gives us negative, the 2's cancel, square root 2 over, here we would get 2 square root 2. And then we cancel the square root 2's, so we end up with a slope of negative 1/2. Okay, and then we need an x and a y value. So again, our t is pi over 4. Let's go back into our original equations. X is 4 sine t, so 4 sine of pi over 4. So 4 sine of pi over 4 square root 2 over 2. Simplify, so that's 2 square root 2. And then the sine, the y is 2 cosine. So 2 cosine of pi over 4. So that's 2 times square root 2 over 2. 2's cancel, so we have square root 2. Okay, and so now we could use y, our point slope formula. Y minus y1 equals m times x minus x1. So y minus the square root 2 equals our slope, which was negative 1/2, x minus x1, which was 2 square root 2. Okay, simplify it. Distribute the negative 1/2. Negative times negative is a positive. 1/2 times 2 square root 2. The 2 and the 1/2 would cancel. And then we could move the square root 2 to the other side. So y equals negative 1/2 x plus 2 square root 2. Okay, so that would be the equation for the line tangent to that curve at that point. Okay, well, that's the end of the review. I hope this helps, and I hope you guys all do well. Alright, and so hope to see you guys soon. Have a great day.